Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Seruni Elsa-ZAHRA from class 4A1. In this learning video, I want to explain vector material. Let's go. Material 1. Translation of plane. If you translate the graph y equal E x z plus b x y through a distance c in the y direction is new. Equation is y equal a x for 2 plus bx plus c. In general, if you translate the graph y equal fx distance c unit in the y direction, is equation becomes y equal fx plus c. A practical way of doing this to draw the graph on a transparent sheet page over a coordinate grid, and to move this sheet up the grid by c units. The essential feature of a translate is the sheet move over the grid without turning. A general translation would move the sheet k units across and l unit up the grid. This is shown Fig. 1, where several points move in the same direction through the same distance. A translation is called a vector and is written matrix K sampai dengan L. For example, the translation of y equal fx described above would be performed by matrix OC the vector. Similarly, the vector K O performs a translation of k units across and the y direction. In practice, the drawing several arrows as in Fig. 2 is not a convenient way of representing a vector. It is usual to draw just a single arrow as in Fig. 2, but you must understand that the position of the arrow in x y minus plane is of no significance. This arrow is just one if infinitely many that could be drawn to represent the vector. You might make uses of vector in another context. For example, mechanics uses velocity vector, acceleration vector, force vector, and so on. When you need to make the distinction, the vector described here are called translation vector. Next slide, 2-vector algebra. It is often convenient to use a single letter to stand for a vector. In print, bold type is used to distinguish vector from number. For example, in P equal KL, P is a vector, but K and L are numbers. Call the component of the vector P in the X and y direction. In handwriting, vectors are indicated by a wavy line underneath the letter P equal KL. It is important to get into the habit of writing vector in this way so that it is quite clear in your work which letters stand for vector and which stand for number. If S is any number and P is any vector, then SP is another vector. If S big for 0, the vector SP is a translation in the same direction as P but S times as large. If S small for 0, it is in the opposite direction and ends as time as large. A number such as S is is often called a scalar because it usually changes the scale of the vector. The similar triangle in Fig 3 so that SP equal SK SL. In particular, minus 1P equal minus K minus L, which is a translation of the same magnitude as P but in the opposite direction. It is denoted by minus P. Vectors are added by performing one translation after another. In Fig 4, P and Q are two vectors to from their sum. You want to represent them as a of rows by which you can trace the path of a particular point of the moving set. In Fig 5, P is shown by an arrow from WY U to V and Q by an arrow from V to WY. Then when the translation are combined, the point of the sheet which was originally at U would move first to V and then to WY, so the sum P plus Q is represented by an arrow from U to WY. Fig 5 also show that if P equal KL and Q equal MN, then P plus Q equal K plus M L plus N. So from the sum X plus P, the translation are performed in the reverse order. In Fig 6, K is now represented by the arrow from U to Z and signs U V W Z is parallelogram. P is represented by the arrow from Z to WY. This shows that P plus Q equal Q plus P. This is called the cumulative rule for addition of vector. Next slide. 3 basic unit vector. If you apply the rules of vector algebra to a vector in column form, you can see that P equal KL equal Q plus 0, 0 plus L equal K 0 plus 0 L equal K 1 0 plus L1 L01. The vector 1 0 and 0 1 which appear in the last expressions are called basic unit vector in the x and y direction. They are denoted by the letter I and G, so P equal KI plus KI plus LG. This is illustrated by Fig 7. The equation shows that any vector in the plane can be constructed as the sum of multiples of the two basic vectors I and G. The vector Ki and Kg are called the component vector of P in the x and the y direction. You now have two alternative notation for doing algebra with vector. For example, if you want to find 3p minus 2k, where p is 2, 5, and k is 1 minus 3, you can write either 3, 3 to 5 minus 2, 1 minus 3 equal 6, 15 minus 2 minus 6 equal 6 minus 2, and 15 minus 6 equal 421, or 3 to I plus 5g mean 2i minus 3g equal 6i plus 15g minus 2i minus 6g equals 6i plus 15g minus 2i plus 6g equals 4i plus 2lg. You will find that sometimes one of these forms is more convenient than the other, but usually it makes no difference which you use. For position vector, if E and F are 2 points on a grid, there is a unique translation which takes you from E to F. This translation can be represented by the arrow which starts at E and ends at F, and it is denoted by the symbol vector EF. Some books use EF in bold type rather than vector EF to emphasize that it is a vector. However, although this translation is unique, its name is not. If G and H are two other points on the grid such that line EF and GH are parallel and equal in length, so that EFHG is parallelogram. Then the translation vector EF also takes you from G to H, so that it could also be noted by vector GH. In a vector equation, EF vector EF could be replaced by GH vector GH without affecting the truth of the statement. The next slide vector written like this are something called displacement vector, but they are not a different kind of vector, just translation vector written in different way. There is, however, one especially important displacement vector. This is translation that starts at the origin 0 and ends at a point A. Vector O I in fig 9. So that vector OI equal vector EF equal vector GH. The translation from 0 to I is called the position vector of I. There is close link between the coordinate of A and the component of its position vector. If A has coordinate the u v, then to get from 0 to I, you must move u unit in the x direction and v unit in the y direction, so that the vector OA has component u and v. The position vector of the point A with coordinates u, v is vector OI equal u, v equal ui plus vg. 5. Material algebra with position vector. Multiplication by a scalar has a simple interpretation in terms of position vector if the vector SA is the position vector of a point D. Then, if S big for 0, D lies on the directed line OI produce, if necessary, such that OD equals SOI. If S small for 0, D lies on the directed line I0 produces such that OD equal SOI. This is shown in fig 9 for 3/2 and S equals -1/2. To identify the point with position vector I plus B is not quite so easy, because the arrow from 0 to I and from 0 to B are not related in the way needed for addition. See Fig 10. It is therefore necessary to complete the parallelogram or ICB as in Fig 10. Then I plus B equals vector OI plus OB equals vector OA plus vector AC equals vector OC. This is called the parallelogram rule of addition for position vector. Subtraction can be shown in either of two ways. If you compare Fig 11, you will see that B minus I is the displacement vector IB. To interpret this as a position vector, draw a line OE equal and parallel to IB, so that vector OE equal vector IB, then E is the point with position vector B minus A. Next slide, alternate Alternatively, you can write b minus I as b plus minus I and then apply the parallelogram rule of addition to points with position vector ben minus I by comparing fig 11 and 12. You can see that this leads to same point E. Example, points A and B have a position vector A and B. Find the position vector of I, the main point M of IB. B, the point of 3 section T such that IT equals 2 per 3 IB. Answer I. Method 1. The displacement vector IB equal B minus I, so vector I am 1 per 2 B minus A. Therefore, M equals vector OM equals vector OI plus vector AM IM plus equals A plus 1 per 2 B minus A equals 1 per 2 I plus 1 per 2 B. Method 2. If the parallelogram OICB is completed, C fix 10, then CI plus B since the diagonal of OICB bisect each other. The midpoint M of AB is also the midpoint of OC. Therefore, M minus C minus M equals C equals I plus B equals A plus BB. The first method of A can be modified. The displacement vector IT equals 2 per 3 vector IB equals 2 per 3 B minus A, so T equals vector OA plus vector AT equals A plus 2 per 3 B minus I equals 1 per 3 I plus 2 per 3 B. The result of the example can be used to prove an important theorem about triangles. Thank you for watching.